Good morning, everybody. So I'm Eric Darve, and it's my pleasure to introduce our speaker this morning for the plenary lecture. So we have Marta Delia. She's a adjunct professor at Stanford and also currently working at Atomic Machines. And so she's going to talk about the applications of graph neural networks so she'll cover a number of applications.
All right. Good morning, everybody. Thank you for showing up so early this morning. It's an honor to present to this community, and I'd like to thank the organizers and everybody behind USNCCM for the impeccable organization. So thanks, Eric, for the introduction. Today I'm going to talk about some recent work on the use of graph neural networks in different scientific applications, but in particular, I will focus on a work that I'm doing at Stanford in collaboration with SLAC for particle accelerators. All right, so this is a brief outline of my presentation. I will start by talking about industrial and scientific design and about the type of surrogates that we're after in design settings. And then I will talk a little bit about the use of graph nets in physics simulations. I will provide some examples beyond particle accelerators that just to set the stage a little bit. And then after introducing the particle accelerator problem, I will present some end-to-end results, which basically means creating surrogate maps that go from an initial state of a particle cloud to the final state, and then autoregressive results to track the evolution in time of the particle cloud. And then I will say something about what we're planning to do next and just talk about some conclusions, more general conclusions. All right, importantly, these are the people that contributed to this talk. Tiffany, first of all, she's sitting here. She's a PhD candidate at Stanford ICME. She's the main contributor of the particle accelerator work. But to this work, also other people that contributed are Orly and Eric Kropp from SLAC and Eric Darve, clearly from Stanford. As I said, the work that I'm going to present is not just about the particle accelerator, but here and there I will mention other works, and I want to recognize the work of Leonardo, who's right now a PhD student at ETH, but was my master's student last summer, and he worked on GNN surrogates. And Rini Gladstone, that at the time was a PhD student at UIUC. Co-advisor Heidi Medani is here, I think, and is also co-author of this work. All right, so ultimately, we're interested in solving design problems, which are very common in scientific and industrial settings. And in this context, what we have to do usually is to solve an optimization problem, a constrained optimization problem, where the constraints are multiphysics equations. They can be very complex, highly nonlinear, coupled, multi-scale, multi-phase sometimes. So clearly there's a time and cost concern because we have to solve this system of equations at every iteration of the optimization problem. And so typically what we're looking for is to find a way to substitute these expensive simulations with surrogate models of some form. So what are the surrogates that we're after? Clearly, we want them to be cheap, but also accurate. And I'm putting cheap in bold because lately we tend to try to surrogate everything without really thinking about how much time it takes to train something, because we need a good and curated data set. So being cheap for real is very important. And something that we want, and that sometimes makes them cheap, is that they generalize across all possible scenarios that the optimization may ask for. As we search the design parameter space, we want to make sure that these surrogates can solve accurately for every point in the parameter space. And this means that we want surrogates to generalize, for example, with respect to operating conditions, environment conditions, boundary initial conditions, and geometry, which in design context, especially in the industrial setting, is probably the most important thing. Finally, we would like these surrogates to be differentiable because we have very efficient gradient-based optimization methods, and differentiability clearly is mandatory. So I want to make a distinction because when we solve design problems or optimization problems, typically we need a map from design parameters to the objective function, to the quantity of interest. And one could just create a map, even a differentiable map from design parameters to the quantity of interest, and forget about the simulation of the whole field. But one can also create a surrogate for the whole field and then infer from that field the quantity of interest. And today I'm going to focus on the latter case where we're after full field surrogates. So the slide is going to be very basic for a huge percentage of the people in the room, but I just want to set the stage and explain what type of surrogates we're after, just in terms of their architecture in a way. So due to the differentiability ask, we are going to consider neural network, which are data-driven surrogates, highly differentiable. And we want neural networks that truly act as substitutes of traditional simulation tools. Here I'm reporting probably the simplest, most popular equation that we published papers on, a classic deep grad operator. You may pick your favorite discretization method. And what we have here, when we, for example, we use finite elements for any diffusion coefficient, forcing term, geometry, computational domain, we get a solution. And forcing term here, for example, we get a solution over the whole domain. So we want our neural network to behave in exactly the same way, which means we want the neural network to be able to take as input any diffusivity, any forcing term, and any geometry, and predict the value of the solution at every point in the domain. So this means that input and output of the networks that I'm going to consider today have the same size of the computational domain. I'm saying fully data-driven because in a way, in what I'm going to present today, I'm not going to embed physics explicitly. And so the way the training problem is solved is simply by solving an optimization problem where we minimize the difference between the output of the network and correspondence of certain input parameters and the ground truth, the solution that we have. So given input-output pairs, we train the network in this way. All right, now that we have set the stage for this, clearly we have to ask ourselves what we want from the network. And given that inputs and outputs live in the computational domain, we have that the network nodes represent the degrees of freedom of the simulation. And we want to be able to capture the relationship between nodes and degrees of freedom directly. People that know me know how much I appreciate non-locality and the solution of multi-scale problem. And for this reason, we would like network to be inherently multi-scale, which means being able to capture both global and long-range interactions. We also, I showed the finite element mesh triangulation. So this is common in a lot of applications, but one might also pick particle methods to solve a problem. And so we want our surrogates to be able to deal with these data representations. So we want to be able to deal with irregular data. We also want to find a good compromise between complexity or expressivity and stability, because sometimes complexity of a network might lead to instability issues. When it comes to interpretability, I think this is a loaded term in machine learning, and I would say there are maybe two types of interpretability which are both good. The first type is by looking at the network, by analyzing the network, its layers, we can infer something about the physical system, which is clearly good because it provides insights. And the other form is recognizing in the network some mathematical and physical objects that we are familiar with. And the typical example is neural ODEs. And this type of interpretability is very good because we are trained in scientific computing and we recognize the object and we know how to analyze it, and so we can control it. Finally, we want to be able to embed some physics in our network, at least as much as possible, but also my preference is to add it in the cheapest way possible. And there are different ways. We can modify the architecture so that it naturally embeds some properties such as invariances, but we can also add to our optimization problem, to the training problem, an enforcement of a certain equation that we are aware of. So now we get to graph neural networks. And I would say that graph neural networks can satisfy naturally some of these properties, the one that have a green check mark, but with appropriate changes, we can also get to satisfy other properties reported here. And I realized I skipped resolution independence, which basically means that we would like the network to be accurate across resolution of the data. And this is very useful because you may want to train on coarser data and then still be accurate on finer data. This is also possible with graph nets by structuring the network in a certain way. When it comes to physics, I'm crossing the residual of the equation from the training objective, and this is simply because this is not what I'm gonna present today. This is clearly something that can be done, but it does make the training more involved because typically when you're in situations like this, you're gonna have to find a good balance between the two terms, but it's certainly a possibility. Okay, so let's start from a very general introduction, which is going to sound trivial to all of you, but again, let's set the stage for GNNs. So clearly they're based on graphs, which are a collection of nodes connected by edges, and they might have global attributes that apply to the whole graph. There are different types of graph nets. The idea, though, is that we go through several modifications of these graphs. These modifications are, and the different stages of the graph are the different layers of the graph networks. And there are different ways to go from one graph to the other, and the one that I'm considering today is by message passing. And this little drawing here just explains how message passing works. Just for a subgraph, what we have is that we update the information on edges, typically by using a smaller neural network, a feed-forward simple neural network, typically an MLP. And once the edge is updated and all the edges going to a node are updated, we have some sort of aggregation of these messages that can be done by summation, mean, different functions. And then we update the information of the node based on the information that we get from the edges. It's worth at this point mentioning a message passing graph neural network that I believe became very popular in scientific application, and is the mesh graph net architecture that was introduced by DeepMind now 5 years ago. So this is going to be the baseline or the base architecture that we consider in the application that I'm presenting today. So I'm going to spend a couple of words just describing it. So the idea is to start clearly. We can deal with irregular data. They can be mesh points, cloud points, a point cloud. We construct a graph representation. In some cases, this is very natural and straightforward. If you think about P1 finite elements, which is something that we use in these simulations, that it's really straightforward to go from mesh to graph. Then we have the graph prediction, and we can go back to mesh space or point cloud. So when it comes to the graph prediction, the architecture that we use is a encoder, processor, decoder type of architecture. This can be done both for static problems and time-dependent problems. What I have here is for time-dependent problems. You have a graph at a certain time or a solution represented by the graph at a certain time. You encode all the nodes with a certain network, all the edges with a certain network, so you have a latent graph. And then you perform your favorite number of message passing blocks or steps. You have a processed latent graph, and then you decode the nodes into the original space, the physical space, and you have your prediction at the following time. The way you propagate in time, there are different ways, but typically, let's say, graph at time t+1 is your solution at that time, and you use it as the input to the same network, and you keep iterating until you cover your whole time interval. So now that I've introduced this base model, I want to provide an example that is truly a straightforward application of the architecture that I just presented, maybe with small modifications, but this is an example for a single physics, single variable, scalar variable architecture that shows how effective these architectures can be. And in this application, and this is the work done also at Stanford for laser-based additive manufacturing. I'm not going to talk about the application itself. I presented that in a mini symposium, but here I just want to focus on a surrogate for the temperature. Surrogates for temperature in laser-based applications are very important because they allow to track thermal effects as the laser is fired. So the idea here is we have a 3D geometry and we are discretizing it with a triangulation, and we have a laser firing on the top surface. That's going to be our heat source, our boundary condition. And the simulation that we do with finite elements predicts the temperature field at every time step as the laser is firing. We consider in our data set different type of laser trajectories, zigzag, vertical, horizontal, spiral. And the idea is to make it efficient, clearly, to make it useful, is that this surrogate that we want to create for the temperature generalizes to any type of architecture, to any type of laser trajectory, even when we train it just on one type of trajectory. And this is because it makes it efficient. So what's the graph net that we built? As I said, we're using P1 finite elements. The vertices of the mesh become nodes. The sides become edges. Very straightforward. Since we're considering evolution in time, the inputs are the temperature at every node. At the previous time step, we also add the coordinates of the node and the forcing term at the following time step, because that's what we use for the prediction. And the edges only contain geometric information, such as signed distance between points and Euclidean distance between points. We are predicting a temperature which is positive, and so we slightly modify the original architecture that predicts the difference between subsequent time steps, and we just predict the variable of interest at the following time step. And we also consider as a last layer an activation function that ensures that the computed variable is positive. Given the fine time step that we're using, we coarse-grain the data set in time so that the time step of the graph net is not the same as the one of the simulation. This is very typical for several reasons that I'm happy to talk about. And another thing is the loss function, the one that I introduced earlier. There is a slight modification that is very typical at this point for problems in time. So first thing, when we pass the input to the network, we perturb it with some Gaussian noise. And this is because as we follow the evolution in time, it's very likely that there's going to be error propagation, error accumulation. And so we're trying to teach the network that it might get solutions that are not accurate, but the network still has to be accurate in its prediction. Another way to make sure that the network can generalize in time, can propagate well the information in time, is to consider several steps of the network in the loss function. So that basically in the loss function, we don't just apply one step of the network, but k steps of the network. So, oops. These are case steps of the network that predict the solution at time t n plus k, and so we compare this prediction to the ground truth at that time step. And this simply ensures that we are teaching the network to not accumulate error in time. All right, so this is just one example, one sample in our validation data set, target, temperature, predicted temperature and relative error, this is the L1 relative error that is always of the order of more or less 10 to the negative 3. And this is consistent across all the trajectories that we consider that were not in the training set. Another thing, since I mentioned, adding noise to the input and using a multi-step loss function, this is just a comparison of L1 and L infinity error. The scale is not super visible, but this is 10 to the negative 2, this is 10 to the negative 3. The network is improving of more or less 1 order of magnitude. All right, so this is a very straightforward application of the network for, I would say, a simple problem, single physics, single variable, and it shows how well these networks are performing in this setting. The particle-accelerator application is way more complex than this. But before getting there, I want to talk about challenges. Like I just showed an example where everything works super nicely, but this is not always the case. There are settings in which the plain GNN is really not a good choice. And one is, for example, static mechanics, or in general, you can think of elliptic PDEs where the solution at a point depends on the solution at every other point. The information propagates immediately across the domain. And so while graph neural networks communicate layer by layer, but immediate neighborhoods, what we need with these problems is instantaneous propagation of the information across the domain. And to reach this, we need, especially with fine meshes, we need a lot of layers, and this can lead to a more expensive network to train and maybe potentially instabilities. And so in this case, we need to find a way to make the propagation of information throughout the network, throughout the nodes of the network, to make it faster. And so in one of the works that I mentioned at the beginning, we decided to introduce a couple of ways to make sure that the information propagates faster. And one, I call it multi-grid GNNs because I think it's intuitive for this community. And it's basically applying a sort of multi-grid method as we go through the layers of the network. And this basically means as we propagate the information, we coarsen the graph. So that by coarsening the graph, the information can propagate far in the domain. This is obtained by combining mesh graph nets with pooling operations, and in particular with the GraphU net that does exactly what I just explained. It coarsens the mesh and then goes back to the original resolution. GraphU nets were introduced for, I believe, classification purposes, but they can be useful also in scientific settings. But we need to be careful as we coarsen the mesh and as we go through these pooling operations because we might end up with graphs that are disconnected. The original GraphU net, for those of you who are familiar, uses top K algorithms for pooling, and you might end up with disconnected graphs, which is really not good for mechanics applications. So this is one example. The network turned out to be way more accurate than the baseline. And the second case is the edge-augmented graph neural network that is very accurate, but is also more expensive because basically we're adding random edges throughout the domain that clearly connect points that are far from each other. So we have fake edges. And we added them in a random way because we even tried to find, I would say, a more structured way of doing it, but the random addition of edges worked really nicely. Okay, so this is for static mechanics. In computational fluid dynamics, I mean, these networks were introduced in the context of computational fluid dynamics, but in industrial setting, it happens very often that customers ask for steady CFD, so for steady problems. And in this case, the information, if you think of a pipe, the information that you have usually is the inflow information, and everything else is no-slip condition and some sort of homogeneous Neumann at the output, which means the only information that you provide as an input to the network is the boundary condition in a very small part of the domain. And it's very hard to propagate this information across the domain in one shot. So I mention it just as something we need to be careful about if we want to use these networks. When it comes to unsteady CFD, something that is important is the directionality of the flow. Clearly, the flow is going in a certain direction, and graph nets treat every node or every edge actually in the same way. So the information that goes from I to j is the same as the information, has the same importance of the information that goes from j to I. And so something that we worked on that I'm not going to cover today is the use of a graph attention mechanism that basically puts more emphasis on those edges whose direction goes, that go in the same direction of the flow, basically, so that we put more emphasis on where the information is actually going in the simulation. But as I said, this is not something that I'm going to cover today. But I wanted to point out that it's not always super easy and straightforward to apply this type of neural nets. All right. So in these last 15 minutes, I'm going to talk about the use of these networks in the context of particle accelerator simulations. And as I said at the beginning, our ultimate interest is really in design. And so the idea is to develop surrogates for the propagation of particles in time through the accelerator with the goal of doing beam customization and with the goal of finding configurations of the accelerator that weren't available before, that maybe just by intuition you cannot come up with. All right, so what are these objects? And this is a very short slide to summarize what is happening. So these are machines that use electromagnetic fields to propel particles to reach high speeds and high energies, and they have several applications. Probably a common one is in medicine for cancer treatment. I'm listing here the key principles that determine the physics of these accelerators, which is a very complex physics. Particles are accelerated by electric and magnetic fields according to the Lorentz force. The energy gain is obtained by oscillating electrical fields, and this happens in the radio frequency cavities that induce oscillations of the particles. And the beam dynamics, which means the particle trajectory, the way the beam bends, focuses, defocuses, and how stable it is governed by the presence of magnetic fields or magnets that induce magnetic fields, and some bend the beam, some focus and defocus the beam. And I have some example of how the presence of these fields changes the particle shape throughout the accelerator. Some facts. Here we have a lot of parameters to control and or design, and a lot of variables to observe. Clearly, actual experiments are very expensive, and so simulations have been introduced. Simulations are expensive as well. And I have an example here of a simulation that, even though accurate, took a lot of time on many cores to be computed. So why are they so expensive? Well, because it's a coupled system of equation. Of course, we have the Maxwell's equation of motion, as I mentioned earlier, governed by the Lorentz force. There are many nonlinear and collective effects. So this simulation turned out to be very, very expensive. And given the setting that I just presented here, clearly this creates a huge opportunity for machine learning to make a difference. So it's not that we're after the application that is going to prove the GraphNet work, but we do believe that this is an application where the surrogates can make a difference. There is previous work. The PI orally that I mentioned earlier looked into these surrogates before, obtaining very good speedups. What we want to do is to improve the accuracy of these surrogates, maintain the speedup, and also we want to be able to track with the surrogate the evolution of the particle cloud in time. And this is done with the autoregressive surrogate that I mentioned earlier, the reason why one might want to follow the trajectory in time is because there are design parameters that are time or location in the accelerator dependent, and by having the full evolution, it's easier to learn these parameters. We have two goals at this point. As I said, we want to build surrogates that are substitutes of the very expensive simulations that I introduced. And we're going to look at two surrogates. One, we call it end-to-end prediction, which simply means from time step 0 to time step n to the very last time step in one shot. And then, as I mentioned, we want to follow the evolution in time. So what type of data do we have? We have point clouds. Each point in the cloud is characterized by its position in 3D and by the momenta. All these values are later normalized, and we generate these point clouds with the simulations provided by SLAC in correspondence of very different initial conditions, but also in correspondence of different accelerator settings. So typically we have 6 machine settings. These are constant parameters. These are the parameters that we use to set up the machine. Something important, though, that will be important when it comes to the evolution in time is the fact that these machine settings induce changes in the electric and magnetic fields throughout the accelerator. So this is a function of z, which is the variable that crosses the accelerator. And so we can see that as the particles move, the fields are changing. And so this becomes relevant when we consider evolution in time, so through the accelerator. So 5 minutes, interesting. So this is, again, the usual architecture that I introduced before, and I'm representing it here for the end-to-end map. We go from the graph at time 0 to the graph of time n directly. There's no iteration. And what we do in this case is to append to every node the 6 machine settings. So they're simply appended. The nodes have positions and momenta, and the edges only have geometric information as before. When we do the time advancing scheme, then we go back to having the autoregressive network where we take the graph at the next time step and use it as the input for the next prediction. Given the short time that is left, I just want to mention we tried other architectures, and I have a slide where we have the comparison. It's very intuitive in this case, since we have particle clouds, so to think of point nets, which were developed for clouds, for different purposes, though. And we did implement these, and they didn't work very well. And the reason is because when we use point nets, basically, we don't consider interactions between input points up to here, where we go through several node-wise transformations until we do a max pooling operation that condenses all the information in one scalar. And every point is basically treated independently, and point-to-point interaction is not considered. So this is something that graph networks clearly resolve by considering point-to-point interaction. So this is a comparison slide where I'm reporting what I would call a phase plane, position versus momentum in X, Y, and Z. We have the target in the first column, GraphNet, our architecture, and other architectures, graph transformer and point net, and a baseline, which is the graph convolutional neural net. And as you can see, just from the shape of these, shape of these graphs, we have that the GraphNet is the one that is the closest. I also put it the closest, but it's the one that is the closest in shape to the target. This is the relative emittance in the x direction. It gives some information about the shape of the point cloud. It's an important variable in this case, and we can see that the relative error for the graph net is the lowest, while point nets definitely don't do a good job here. So this is a further confirmation. It confirms our intuition that graph nets, message passing graph nets are a good choice. And so we're ready to move to the time-dependent problem. And intuitively, one could think that you can use exactly the same architecture, appending the constant machine settings to every node and providing the time as an additional information and just predict the time evolution. This is not working because we cannot expect a single network to predict the whole evolution in time because the regimes are changing. The regimes are changing according to the graph that I introduced before, where we have an evolution of the electromagnetic fields. So what these changes imply is truly different regimes as we move throughout the accelerator. So in a certain interval, we have a defocusing effect, then we have a rotation effect. This is between steps 10 to 20. Between steps 20 to 30, we have a focusing effect. And then when we are in this regime, we don't have any changes in the shapes. So clearly, we need to provide this information to the network. This is known, this is given information. And what we decide to do is, as a first step, and this is very much an ongoing work, is to basically train a model per regime and make sure these models are accurate enough so that then we can concatenate them and predict the whole evolution in time. And so we train a model in every interval that you see here, and we don't just provide the constant machine settings, but we also provide how the machine settings induce changes in the electromagnetic fields as we move throughout the accelerator. We append these values to the networks and to the nodes of the network, and we train different models in different time intervals. And these are some results. The notation of the graphs is the same. We have the x, px, y, py, and so on. And what we can see is that these models, as we roll out within their interval of time, they remain accurate. So here we're reporting both the MSE and the relative error in the emittance for all the variables. Our target is to be below 1% of accuracy. And all models, and I'm reporting just 2 of them in this case, do a good job at staying around that accuracy. What I didn't mention is in these models, we also use a loss function that is a multi-step loss function with 3 steps, and we also provide input noise to the network during training. All right, getting to the next steps of our work. We clearly want to extend the autoregressive architecture to different machine settings. We would like to take care of long-range effects and multi-scale effects more explicitly, possibly by introducing pooling layers, just as in the mechanics example. And we would like to enforce the physics more effectively. We know that there are point-to-point interactions, and we want to make them more explicit, possibly in the edges. And clearly, long-term, as I mentioned, we want to use these architectures in design settings. I see that Eric is standing, so I'm just going to drop my conclusion slide here. And the single message is that these networks have a lot of advantages, can be applied in a very straightforward way, but there are also several open challenges that we have to be aware of. So with this, I thank everybody for being here, and I'm happy to answer any questions.
All right, so thank you very much for this great presentation and showcasing graph neural networks on two very different applications. So we just have a couple of minutes for question and answers. I guess I will just start with a first question. There's classical techniques to solve physical systems with PDEs and so on. And of course, nowadays we have data-driven methods like deep neural networks and convolution neural networks. So for example, the first problem you showed with the temperature, solving the temperature field, could be solved using, for example, GNNs and techniques like this. And so you presented today graph neural networks. So I was curious about, what sort of applications do you think are most suitable for graph neural networks? Or when should you think about using graph neural networks to solve your problem?
Yeah, hard question to answer because I think it's very problem dependent. Especially now that we have modifications of traditional solvers that can run very, very quickly on GPUs. So the first question is, do I want to use a network or do I want to stick to my traditional solver? And in some cases, the answer can be stick to the traditional solver. And this can happen with very simple systems where you don't have multi-physics effects, multi-scale effects, where things are easy in a way. But I feel like the moment you have a very complex system with a lot of physics going on and you have the opportunity of using a network just with the like what we did with the particle accelerator, that in one network can cover all the complex physics that is going on, that is certainly powerful and it does save a lot of time. Then when it comes specifically to graph nets, clearly, you mentioned GNNs. GNNs kind of constrain you to have structured grids. So, and it's very rare, I would say, in many applications to have structured grids. The moment you use finite elements, particle methods, you have unstructured data, and so GNNs are clearly very powerful. So in those cases, I believe that's the right choice. And then, as I mentioned, they're very good at capturing multi-scale effects and point-to-point interactions. And sometimes we do know about the physics of point-to-point interactions. We can embed it in the network. And so I think that's where they become more powerful than other architectures.
Okay, great. So questions maybe from the audience? So I think we have a mic. Yeah, thank you.
Marta.
Yeah, it's working.
Very impressive work all around. Can you highlight a little bit about where geometry comes in? I guess it's not so clear in the beam problem because the beam geometry is the same. I mean, you're changing boundary conditions and all that, but a little bit more on the geometry side.
Yeah. In this work that I presented, and this is a great point because really in design settings, especially in industrial design settings, you're solving a shape optimization problem or a topology optimization problem. So what we did here, this was a mechanics problem, and we wanted, and it was in design settings, we were doing shape optimization. And the idea was to train a model that could generalize to unseen geometry that are highly nonlinear, and I wish I had the slide, and that would go through a lot of changes, even in terms of scale. Also, we wanted to generalize with respect to boundary conditions, and not just the value of the boundary condition, but also the type of boundary condition. And so I have to say this network worked so well. We were using a type of hot encodings, and basically we would add a tag to identify the Neumann or Dirichlet or Robin boundary condition, and they could generalize very well to different values and type of boundary conditions and across a huge range of geometries. And I think this is something very powerful about GNNs because they're absolutely independent even of the dimension of your mesh, because every node and edge is treated in the same way. And so it doesn't matter if you get a new mesh with a different number of degrees of freedom. They work very nicely anyway.
Any other questions? I think there's another question on the left here. Thank you.
Very nice talk. So you mentioned about this rotation translation should be identical in physical simulations. So in your work, how you treat these issues?
Which is, I didn't
regarding
hear.
the rotation translation.
Oh, yeah. So in this work, we didn't even change the architecture. We basically did some data processing where we basically transformed every single geometry in principal coordinates. And then once you do that, the network doesn't know that that specific sample is coming from, a rotated or translated geometry. All the samples live in their principal component space. And we did tests only using same geometry, rotated and translated, and clearly the network behaved in exactly the same way. But you can definitely embed those type of invariances in the network just by forcing, for example, the fact that the network is translation invariant. So it can, but in this work, that's what we did.
All right, so I think we're out of time. I want to give you a little bit of time to have your coffee and transition to the next sessions. So yeah, thank you, Marta, for giving this great presentation and overview of graph neural networks and these two amazing applications. Thank you.